Today we want to keep thinking about limits and continuity and differentiability. Continuity is the function connected? Are the values of the function connected? Differentiability is about, are the values of the function connected smoothly? This all has to do with with limits. We needed limits to be able to make these descriptions. Intuitively, limits are just asking the question, where are things headed? Continuity and differentiability have to do with, are things headed to the same place from both sides? That's really what it comes down to. Are things headed to a particular place from both sides? Continuity is about the values of the function. Are the values of the function from the left headed to the same place as the values of the function on the right? In the category of differentiability, this takes it one step further. Are the slopes of the tangent lines headed to the same place? So remember that in continuity, we have a discontinuity when there's a gap in the function. A discontinuity happens when there's a gap in the function. I guess I should say the graph of the function. Do that. If there's a gap in the graph of the function, that's a discontinuity. The function is discontinuous at that point, because either the function is not defined there or the limit doesn't exist, because going to the left and coming from the right are going to different places. So continuity is about, is the graph connected? Differentiability is about, is the graph smooth? We say smooth because the place where a function is not differentiable, that means we're going to have a corner. So not differentiable at corners. Discontinuous because the value going in is not the same as the value coming out. Differentiability is that the slope going in is not the same as the slope going out. So that means corners. In the graph of y equals absolute value of x, the slope coming into 0 is -1. The slope coming out of 0 is +1. So we have this corner, this sharp corner at x equals 0. This is what's not smooth, not differentiable. So we calculate, we set up the differentiability of a function by looking at the limits applied to a slope. That's what started this whole discussion off. You recall back in last week, what started this whole thing was, what's the slope of the line tangent to a function at a point, at one point? The problem we ran into is that slope calculation wants 2 points, but we want the slope at 1 point. We approximate that with a secant line using a second point that's nearby, and then we just made nearby smaller. Then we brought in the idea of limits and said, make nearby approach 0. What happens to the slope? So we say that a function f is differentiable at x equals c if and only if Monday, so I can't narrate and write at the same time. A function f is differentiable at x equals c if and only if the limit as h goes to 0 of f of c plus h minus f of c over h exists. Here we're talking about a limit. Limits can have value. If they don't have a value, we say the limit does not exist, DNE. If this limit exists, then we say that the function is differentiable. All we're saying is that we can calculate one slope at the point. That's all that's going on here. We can calculate the slope at that point. All we're saying is that we can calculate the slope of the line that's tangent to the function. There's one tangent line there, and we can find its slope. Notice that in our y equals absolute value of x, we can't do this. The limit's going to be different from both sides. Coming from the left, we're going to calculate a slope of -1. Coming from the right, we're going to calculate a slope of 1. That limit doesn't exist. So the absolute value of x is not differentiable when x is equal to 0. We have a name for this particular limit. We say that this is the derivative of f at c. And we have a notation for this because this is math class, and we have notation for everything. Our notation is to write f and then put an apostrophe and then at c. Instead of f of c, it's f prime at c. That's how we pronounce that symbol. So we say f prime at c. I will probably start saying f prime of c. We're plugging into a function. And when we plug something into the function, we say f of c. And so this is f prime of c. That's with proper enunciation. As you know, this is f of c, but that quickly becomes f of c. F of c. Just put a little different emphasis. And then we'll pronounce this f primacy, because we cram all the words together. But that's f prime of c. We say this is the derivative of f at x equals c. So f prime is the derivative of f. F prime of c is the slope of the line tangent to the function f at x equals c. We have a function called the derivative, and that function tells us the slope of the line tangent to a curve at a given point. That's one of our big questions in calculus. That's our graph interpretation. The slope, the reason we care about the slope of the line tangent to the function at a given point is that this is telling us the instantaneous rate of change of the function with respect to x at the given point. So in general, why we care. In general, we care about the slope of the tangent line because it is the instantaneous rate of change at the point. How's everybody okay? It only seems like a lot to remember because it's a lot to remember. And you have to remember all of it, all the time, from here on out, in perfect detail. It's not a big ask. Mike, you remember trig? But do you remember all of trig? Do you remember enough of trig? Here's the difference. Does anybody remember the double angle identity for sine? Do you remember that there is such a thing called a double angle identity? That's where you would need to be. Not necessarily at this point in your mathematical career. It hasn't been that relevant. We didn't have good questions for sine of what's the sine of 2 theta back in trigonometry. We just said, hey, sine of 2 theta is 2 sine theta cosine theta. And you're like, oh, okay, why do I care? It's like, well, you don't yet. We don't have a good question for this yet. Then I'm not afraid of these double angle identities. And then the teacher turns into Yoda. Oh, you in me. It'll come up later. So it's not about remembering the double angle identities. It's remembering that there are double angle identities. But like I said, it's only a lot to, it only seems like a lot to remember because it's a lot to remember. How's everybody okay? Let's calculate some derivatives using the definition of a derivative because it's super traditional. Don't at me. I turned off comments, YouTube, so you can't be like, oh, that's a stupid question to ask, because it is kind of a dumb algebra question to ask. But sometimes it's an algebra question that needs to get asked because I don't know what your algebra backgrounds are. Because everybody's algebra background is pretty weak. So let's do some algebra. Is everybody ready for algebra? No, no, you are not. I'm just kidding. It's just an algebra. Oh. Actually, let's start even with smaller question than this. Let's just take all the context out of it. Let's let f of x equal x squared. And I want you to find f prime of 3. And we're going to use the definition of the derivative. So I know some of you are thinking, oh, it's 6 because the derivative is 2x and 2 times 3 is 6. How many of you were like already on 6 because you have secret math knowledge? So like, oh, I had extensive pre-calculus that went all the way into calculus. So I know this. So secretly, that's you being sad. So, oh, come on, do we have to use the definition? I'm like, oh, yes, because this is an algebra problem, not a calculus problem. So f prime of 3 is going to be the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. This is what the definition says we have to do. Remember, we're just calculating the slope of the tangent line at 3 and 3 plus h, or from your perspective, 3 plus h. Actually, it has to be from both sides, so it doesn't matter which way I point. A little bit away. So it's the slope of the secant line where h is some small distance away from 3. And then we're going to make that distance equal to 0. The thinking is going behind this. That's why I want to write this down. We're just calculating the slope. Let's write down what the function is. The function is x squared. So I want the limit as h goes to 0 of 3 plus h squared minus 3 squared, because that's what the function is. F of x is x squared. F of 3 plus h is the square of the sum of 3 and h. It sounds so bad when you have to say it for them to do it, but it's not very. What's the problem in this expression with h being 0? We have discontinuity when h is equal to 0, because this expression is not defined when h is 0. We've already gone over that. You can't calculate slope when there's only 1 point. H equals 0 represents 1 point. And also, algebraically, there's an h in the denominator. I can't let h be 0. Then we're dividing by 0. We've got 0 over 0. It's indeterminate. What 0 over 0 do we have in this scenario? So here's our goal. That h in the denominator is causing us a problem. Let's try and cancel it out. That's our strategy. That's in any time you're doing one of these problems, after you roll your eyes and say, why is the teacher making me do this? H is causing the problem. Let's cancel it out. That's our goal. I'll say H is causing the problem, so we're going to cancel out this H. Our goal is to cancel out that H so we can just let H be 0 and just calculate. That's our goal. So in this case, we're just going to algebra. 3 plus H squared, and then minus 3 squared. So I'm going to have, this is going to be the limits as H goes to 0. At this point, we've written limit as H goes to 0 3 times. I'm approaching your tolerance for writing the same thing over again. We have to keep writing it because we haven't done that yet. So we haven't done that part yet. So you've got to keep writing it. You're not going to want to. You're going to be all mad at me. So I go, do we have to keep writing this? I go, well, if you start learning to cut out some of the steps, then yeah, but until then, no. The numerator is going to be 3 plus H squared. So it's going to be 9 plus 6H plus h squared minus 3 squared, which is 9 all over h. Remember, our goal is to cancel out this h. What's causing a problem now is the 9s. Fortunately, one of the 9s is positive, one of the 9s is negative, so we can cancel those out. And it's just more algebra. And now we're at a great place. Now we're going to be able to cancel out the h because now we can factor out an h. If you're wondering if I'm doing more steps than are necessary, really, to make you keep writing limit as h goes to 0, that only might be true. At this point, we can achieve what we want. I wanted to cancel out that h because I want h to equal 0. I want to be able to say h is equal to 0. Now I can. Using the definition of the derivative, algebraically, the goal is to always cancel out the h. Until you have a problem where you can't cancel out the h and you have to know something else. But that's beside the point. For our nice algebraic functions, that's all we need to do. Think back to the previous example, where we had the limit as x goes to 2 of x squared minus 4 over x minus 2. X couldn't be 2 because that x minus 2 factor in the denominator. But once we cancel that out, we can plug x equals 2 in. The rest of the function, what's left over, is continuous at 2, just like 6 plus h is continuous at 0. What this means is that in Desmos, I didn't have Desmos up. I want the slope of the line tangent to the function at 3. So 3, 9 is the point. So if I draw a tangent line to this function, when x is equal to 3, we should see a slope of 6. So y equals, the point is at 3, 9, so 9 plus 6 times x minus 3. And we can see that at 3, that's where they intersect. And we can see that a slope of 6 is what we want. We see that that line is tangent to the curve. This is the best linear approximation for x squared near 3. We zoom in, we don't see a lot of difference in those functions. If you still see the red and the blue being different, look closer. Any questions? I'm helped out by a little bit by the crappy translation between the resolution on my computer and the resolution in the projector. They're fighting right now. That's why some of these lines are all disappearing. For those of you at home, you can't see how bad it looks on the projector. But if you were here, you'd be like, oh, dude, what is this, a Game Boy? Any questions? Comment? Yes. The 6 plus h, the 6h came from multiplying this out, 3 plus h squared. So so that came from 3 plus h squared. So that's where the 9 plus 6h plus h squared came from. When we multiply that out, we get 9 plus 6h plus h squared. And then that 9 conveniently was canceled out by the minus 3 squared out here. Is everybody okay? Same question, new function, different point, but same question. I need to know g prime of 4. We're going to use the definition of the derivative because that's a tool that we have right now. We don't know the power rule yet, even though I know some of you do know the power rule. You have secret mathematical knowledge, which is okay. G prime of 4 is going to be the limit as h goes to 0 of the square root of 4 plus h minus the square root of 4 all over h. H equals 0 is still the problem here. So our strategy is going to be to try to cancel out that h in the denominator. H equals 0 with this h down here. So our strategy is the same. I want to cancel out that h so I can plug in h equals 0. I want to plug in h equals 0, but I can't because that stupid h in the denominator. So if I get rid of it, I'll be able to. In the previous problem, I had stuff being squared. So if I just multiply stuff out, then no problem. I can just multiply stuff out. And then that square, the 9 squared or the 3 squared, 9's canceled out for me. Left h is a factor of the numerator and everything was awesome. But here, square root of 4 plus h is just square root of 4 plus h. You can't do anything with that. But we have an advantage because it's the square root of 4 plus h minus the square root of 4. Anyone know what we do in this situation? We have radicals, a radical minus another radical, which is, I guess, just a 2. So I don't really need that to be a radical, but I've got radical minus 2. What do I do with that? Anyone have a strategy? How do we deal with these radicals? Now, this is a remnant of algebra. This is something that we have to remember from algebra. So what we can do is, like right now, If I just tell you what the trick is, if I just tell you, all I have to do is tell you what the trick is to this problem right here, how we deal with the radicals, it will make all the rest of algebra like snap into place. All those little bits of algebra that are running around, those loose threads of algebra that you have running around in your head. So if you remember all these little bits, if I do this problem right now, right today, as soon as you see it, it ties all those threads together. It's like magic. I don't understand how it works, but it's like magic. I do this one thing, and all of a sudden, algebra becomes clear. I've seen it happen. Last semester, we finished Calc 1 in like a week and a half afterwards because everybody's like, oh no, we totally get it now. It's like magic. It's like I'm downloading something into your brain. But if I wait any longer to tell you how to do this problem, then we have to go through calculus at the normal rate. And it's going to take 16 more weeks like normal. It's like we have to do it like normal people. So I need to do the magic spell right now and show you how this works. So here's how it works. So we can immediately finish calculus, like almost immediately finish calculus. All I have to do is tell you this answer right now, what to do. So here's what it is. Oh, look at the time. I guess that's going to do it for today. I will see you all on tomorrow. I guess we're going through calculus at the normal rates. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.